Hello, and welcome to this video presentation of my project for 1L. For this quarter in 1L, I set out to learn about 3D graphics and OpenGL with C++. I originally wanted to create a general purpose rendering engine, but quickly settled on instead developing a 3D voxel engine in a similar way to Minecraft, which is what you're seeing in the video right now. The features of this voxel engine are pretty bare bones, but it supports placing and removing blocks as well as an infinitely generating world for the player to build in. Now that you've seen the end product, let's take a look at some actual code as well as discuss some interesting problems I faced during development. As mentioned, I use OpenGL. OpenGL is an open source API that basically allows us to communicate with the machine's GPU. When drawing anything to the screen, all OpenGL is essentially doing is just drawing triangles. It is then our job to calculate exactly how and where these triangles should be drawn, and then fill them in with appropriately colored pixels in order to create a desired image. Broadly, this is done in two steps. First, we feed OpenGL with information about every vertex through a little program called a Vertex Shader. Then OpenGL fills in every triangle through a process called rasterization. Finally, we the programmer write another little program called a Fragment Shader, which decides the appropriate color for each pixel in the triangle. Now let's take a look at how we actually do this in practice. Here we see the code for the Vertex Shader. Initially, we retrieve the information stored in each vertex. The position of the vertex, the texture coordinates, the block type, and the brightness of the vertex. The syntax is a bit funny, as we're telling the shader where to look for this data with location equals. But the main thing to take away here is we're basically just declaring some variables. On lines 7 and 8, we declare two out variables. These are basically just variables that the Vertex Shader passes onto the Fragment Shader, since we can't actually pass this information to the Fragment Shader directly. Next up, we declared these uniform variables. These are simply variables we pass to the Vertex Shader itself once, instead of on a per vertex basis. Finally, in the main function, we calculate the appropriate texture coordinates depending on the block type. It can be a bit of a headache to load several textures into the Fragment Shader, so instead we use a texture atlas, which is basically one big image with all the desired subtextures that we want to use. With a bit of simple math, we can index the desired texture. Now onto the Fragment Shader, which is really incredibly simple. First, we define a vec4 called fragColor. This is the final color of the pixel that will actually be rendered on the screen. Secondly, we receive the two variables that we send out of the Vertex Shader with the in keyword. And then we have a uniform variable for our texture atlas. Lastly, we use the built-in texture function to extract the pixel color at the appropriate texture coordinates, and we multiply by brightness to create the illusion of basic lighting. Brightness is just a value between 1 and 0. Where the closer to 0 the value is, the darker the pixel becomes. And that's basically it for the rendering part. So now we can draw triangles, and when you can draw triangles you can draw rectangles, and when you can draw rectangles you can draw cubes. Here you can see how a block is actually just made up of triangles, with vertices at the corners of the block. This works well in and of itself, but when you have a game world consisting of hundreds or even thousands of blocks, it quickly becomes very inefficient to render every single block on the screen. One way to overcome this is to realize that most block faces in the world aren't actually visible to the player at any given moment. Why should we be rendering blocks underground, for example? So the method I used was for every block in the world to check its neighbor, and only if the block next to it is an air block, or nothingness, would we add that specific block face. Here's an example of a chunk that hasn't been optimized. See how many vertices are being rendered for nothing. And here's a correct hollow chunk. Since the player should never normally be inside the blocks like this, there is no visual difference between the two, but the optimized version runs a lot faster. Overall, there are probably a lot of places the code could be optimized to be more memory efficient and also just run faster. One absolutely crucial optimization that I didn't have time to implement is in the chunking system. Currently, chunks are stored in one big vector, and then accessed like this in the code. This is absolutely terrible and only becomes exponentially slower as more and more of the world is generated. Ideally, chunks should be stored in a data structure that allows for quick access, such as a hash map or an octree. Were I to continue this project, this would be the first thing I'd fix. Other than that, the possibilities for further development are almost limitless. I would like to implement a lighting system so that, for example, blocks that are in a cave are dark instead of being fully lit. This project is also a perfect framework for learning about 3D procedural generation. Currently, the world we see generated is merely unprocessed simplex noise, but it would be fun to develop this further, adding biomes, interesting mountains, caves, and trees, and so on. Overall, I learned a lot working on this project. I learned how to work with OpenGL, and I now have a much better understanding of 3D computer graphics in general. This project also forced me to focus on optimizing my code a lot, which was a unique challenge. There are a lot more things I could talk about, but sadly not in the span of a 5-minute video. So for now, thanks for watching.